So what is the objective out of this session, right? There are two objectives that you guys have come in and joined. So like there are two things that I would really want you to take out of this session. And one is, how do you get an interview, right? Because I mean, if all of you are preparing about system design, there's a likely chance you're looking for it. And I think I can add some value there, right? Because I have gone through this process and I've put in a lot of effort when I was in college and when I was looking for jobs. And I think some of these are really unique. Some of these you may know, but it's probably good to go through. And once kind of I'm done with that, that's not the priority. I'll try to spend 10-15 minutes on that and then move on. Then we'll get into system design, right? And what I want to make sure is that we do understand that in the 60 to 90 minute session that we have, we may not be able to do justice to the all of system design. But the thing that I want to make sure is that we develop this mental model and we have this breadth view, so that when we think about a problem, we think about it holistically, right? That's one of the objectives that I have. So I'll start with what it is like to crack an interview, right? In simple terms, you just need to get an interview and you need to ace that interview, right? I mean, it's simple, but then again, it requires a lot of things in the background, right? First things first, the resume, right? So how many of you over here have a Latex resume or have at least heard of Latex? You can probably just do a +1 on chat if anyone has ever heard about it. I see no. So I see out of 10 people approximately that have joined, only 2 have heard about it. And that's the thing. So a lot of folks just don't know about Latex, and Latex is like, I'll tell you what it is. So like HTML is a markup language, right? So similarly, Latex is some sort of language. It's a document preparation system that people use to create, structured content. It's primarily used in research papers. So if you guys ever write a research paper, you'll likely use a Latex template. And what I'm advocating is, like, when you are making a resume, right, a lot of people just use Word. It's not formatted well. It doesn't look that great. Or they use Photoshop. And then, when you put it on a engine, the keywords won't come up because those are images. So look it up. This is just me giving out some reference that, hey, there's something called as Latex resumes. I've also given a template down there, right? And there are more templates. You can choose one that you think is good, but it makes a difference, right? The first things that go out is your resume, and it makes a difference when you have it structured, when you are following the right format. So for folks that don't know, please make a note. You can use this, right? So anyone has any questions on the resume? Cool. So that's fine. I'll move on to the next one. So how do you identify opportunities, right? And like when I was in college, how do I get that opportunity? How do I get those companies? Because not all of these companies will come to your college, right? And you need to figure out a way to advocate for yourself. And and these are like very generic. Some of you might just think it's obvious, but I'll dive deep more on what each of those mean, right? So when I got a Google call, it was from a referral from a friend who worked in Google. So referrals are at the top of the list, right? So if you have friends, if you have colleagues, if you have alumni, be shameless, reach out to them, because you have prepared that hard, right? So for you to be able to get that opportunity, you need to ask for referrals from anyone you know, right? So coming to the second point, for me personally, what I found is LinkedIn is a great resource. I keep connecting with recruiters, hiring managers, startup founders online. And what I notice is, I mean, it's turned the other way around now. Instead of me searching for opportunities, these guys are reaching out to me. And I think that has happened over a period of time. And one of the reasons why that has happened is because these people are always looking for, hiring managers are always looking for new folks to join their team. So Amazon, Microsoft, Google, they're always hiring. So you need to be connected to the right folks, and you need to search them up online, make them friends on LinkedIn, and, reach out. Some of them will respond, some of them will not. It's okay. I mean, anyways, it's nothing. So for you guys to reach out, that makes sense, right? And the third one is cold emails and calling. This one has like the least impact, but it also works. So when I was looking out for jobs, what I did is I created an Excel sheet, and I had all these like 100 startups in India that I think I want to apply to. And then I started searching for who all work at those startups. And, so I find the recruiters, I found the founders, and I find their email addresses if it's mentioned online, and I just reach out to them. And if I reach out to, let's say, 20 folks, maybe 2 responded. Not too bad, right? So my point being is that people think that they don't have opportunities. And what I'm trying to show over here is that you can create your opportunities, right? Just a snapshot of my LinkedIn connection down. I mean, I have some 2,000 connections on LinkedIn. I mean, I don't even know most folks, but like they seem to be hiring or they seem to be into this industry. And it's just good to reach out and make those connections. You will get those kind of ideas and feed when you have that network. Anyone has any questions till now? None, right? So cool. Right, and I want to skip through this part soon enough. I don't want to cover too much time, but there are some good resources I want to share because I have found these personally to be very helpful. And some of you may know about it, some of you may not. You can take you can get this after the session and maybe see what makes sense for you. So if you're into problem solving, go into lead code interview, but solve problems. And just to give you like a number, like the folks I know who have cracked Amazon, Microsoft, Google, whatever those companies are, right? Like the important thing to see is what they have done to achieve that, right? And if you see them, you'll see like they would have solved 200, 400 problems on all these platforms. And when you have solved that many number of problems, you kind of develop a mental model. Oh, this kind of question maps to this kind of question and you can solve it. I mean, these are very high level things. I'll just skip through them. If you're into mock interviews, highly recommended. I'll go into mocks more just to show you my experience, my growth on how mock interviews help. And then if you want to know more about system design or theory, there are these good platforms. If you want to see interview experiences for other, the companies that you're going to interview for, you can go for Geeks for Geeks, Career Cup. And finally, like we are on AsappJobs. I think Sanchez from AsappJobs is doing like a great job. So if you want something personalized or if you want to, if you want more guided experience, reach out to him. So these are some of the resources that I've shared, right? And what I want to do now is like, before I just jump into system design, I want to show you my growth by doing mocks. And the reason I want to show that is because a lot of people just think that, solving in isolation is going to solve their problem, but really not, because your interviews, whether they're phone, whether they're on whiteboard, whether they're in person, requires you to, have that real feel, right? So what I'm doing here right now that you see on the screen is that so I gave my first ever mock interview on October 9th, and like I'm being very transparent here, like how bad I was and like how that transitioned to something good, right? So if you see things you should work on, the guy says, need to think more comprehensively while considering all the conditions before coding. I mean, that's good feedback. A lot of folks don't get this feedback. They think, they keep asking, where am I going wrong? And once you go do mocks, basically these are just free platforms that are willing to help you. The guy on the other side is in the same boat as you. And I mean, you're going to get really good feedback, right? So October 9th, I get this feedback saying, hey, you need to think more conditions and everything. And then I just do one more because I'm not sure if that's like just one-off bad interview. And then this is another interview that I do on October 10th, right? Just to see how I'm doing. And then the feedback I got is, you need to work on your algorithm and speak out the thought process loud. And that was like a realization for me because like when I used to solve problems, I think I was decent at them. Like if you see, right, they're talking about has good knowledge on data structures, C++ and all that stuff. But I never really thought out loud. So, I mean, in my mind, I can solve that problem, but probably the interview doesn't feel that way, right? And so I took that feedback, and then every time I practiced, I was like, every question that I solve, I'm going to think out loud and assume it's an interview question, right? So then I took a break, and then October 15th, right, I took another interview, and this was kind of amazing because like, I mean, I had already been practicing a lot of questions, but like in a week's span, I mean, I didn't get anything to improve on. And like the guy on the other side was like, all good. You are thinking out loud and you are thinking about the cases. Everything is good. And just to make sure this is not one odd thing, I did another one on October 16th. And then the feedback I get is, your communication skills are good. You can think and talk simultaneously, like, which is great. But then, he says, while coding, you're probably a little tensed. And I think he's probably right. I mean, maybe I'm tensed even now. But then again, right, these are good feedbacks for individuals to learn. Because, I mean, all of us are always looking for feedback on how we can improve and go to the next level. And what I want to really emphasize on is like the mock feedbacks matter a lot. So think about it. This is just some good, I mean, in my personal opinion, something that has helped me a lot. This is after a week again on October 24th. Overall decent, but again, some opinion, right? But you get the idea. So I'm going to jump now to the main thing. But like, if there is one takeaway from this session, I really want you guys to know that no one just knows everything. It's like a process. You need to know the right processes. How do you find those right opportunities? How do you prepare for those right opportunities? And then, just, it just works out in the end, like somewhere. Great. Any questions up until now before we start with system design?
Sanchit, Ravi here. One question.
Yes, please.
For the mock interviews, what is the platform you used? And
Yeah, so it's pramp.com, and nowadays there are more. I used Pramp.
okay.
Let me go back here, and I've shared everything that I've covered in this presentation. I've shared all of them here, right? And for mocks, I used Pramp. Like these days, there are more. I think even AsappJobs has something like that, and even InterviewBit has something like that. My personal recommendation is Pramp was great, but you can also explore and see, where the participation is good.
Okay, sure.
Great. Awesome. So, just wanted to give a brief context on how we are going to cover the session now. So, there are two things, right? I'm going to cover some theory, right, about system design, what it is, why we need to talk about it, and then what are some of those basic concepts. And then I'm going to pick up one problem and try to solve it with you guys. Of course, I've seen the solution, and of course, I have a solution in mind. But we're going to see, how we are thinking about it, how we are modeling it, what are the paths, right, and get that breadth view. I don't think we can do justice to the depth view in this short session, but yeah, that's how we are planning to take it, right? So why system design, right? So let's say you gave those and you got an interview and you aced your coding rounds, and then there's the system design round. And the question is, why do you have that, right? So working in Microsoft for past 3 years, what I've realized is that as a software engineer, you're not just coding, right? There are so many other things, and you own your own service, and then you need to maintain it and think about it holistically. And also, as you grow up the ladder, right? As you come in as a senior, as you come in as a principal or a hiring manager or a group manager, right? The thing to understand is that your coding section is going to reduce, but your system design section is going to increase. How well you understand systems, how well you can understand components, and how well you understand how they interact with each other. So, that's why you have system design, and that's why for those of you in this session who are, somewhere advanced, probably not in your colleges, and with some experience, as you grow, system design is going to become more and more like the thing, right? So, anyone wants to take a crack at what is system design?
It's like, how do we build a system? What all aspects we consider? Like maybe designing a parking lot, those kind of a system when it is not there. How we build that from scratch?
Yeah. So again, there are going to be multiple examples, right? And the important thing to understand is that a lot of these various problems that we solve will use those same abstractions, those same building blocks. So what we want to make sure is that we understand those basic blocks well, and then we know how to club them up and solve the problem, right? Yeah. So basically, whenever we are designing a large system, we need to consider a few things, and like what are the architectural pieces, how these pieces work together, and how we can utilize them. Going to the next one, distributed systems. What does it mean? I already have it here, but if someone wants to talk about it, what their view of distributed system is, anyone wants to take a crack? I already have it on screen. So, right. So when we talk about distributed systems, right, basically there are a lot of things that come into picture, and like some of them are scalability, availability, reliability, right? And what are distributed systems at the end of the day are your service or your executable or your binaries, running somewhere across distributed platform, right? And what you get out of those is some of these things, right? What is scalability? So scalability is the capability of a system or a network to grow and manage increased demand, right? So if you have a service that works for maybe 10 people, does it work for 100 people? Or does it work for 200 people or 1,000 people or 1,000,000 people? That is scalability. What is availability? So availability is the time a system remains operational to perform its required function, right? So for example, if I make a request and then that service isn't available, or maybe it's down for some reason, it's not available, right? You guys must have gone through, you use Twitter or Google, and once in a while it just goes down. So that is availability not being there. And there are numerous. So with distributed systems comes a lot of complexity. Your node might go down, your network might not behave the way you want, and that's where, when you design these systems, you want to think about them and see whether they are available or not, whether they're scalable or not, whether they're reliable or not, right? So reliability is the probability a system will fail in a given period, and in other words, reliability is availability over time, right? Considering a full range of conditions that can occur. So what is efficiency, right? Whenever we are designing systems, when you're solving problem in a code manner, you would think about time complexity and everything, right? Memory complexity. But when you're designing systems, the efficiency changes to something like latency and bandwidth, right? How much time does it take for a request that you made to come back to you, right? That's latency. And how many of such requests can you serve? That becomes bandwidth. So as you scale, you would want to make sure your service is as efficient. Basically, otherwise you have those cost problems and scaling problems, and there are so many projects that just don't scale, and then there are alternatives built. So for a system that is well designed, it would be efficient and well thought through. And of course, in the end comes like whether it's serviceable or manageable or not. So, right, how easy to update, maintain, are there monitoring, alerting, all that stuff. Great. So the next thing that I have here is scale.
Sorry, Sanchit. One question. So
Yeah,
you are
sure.
saying everything will be an iterative architecture. It won't be never be everything in place. It will be always iterative architecture itself.
It depends on the scale that you're trying to solve, right? For example, if you're a startup and you just want to do a prototype or a proof of concept, maybe it's too early to think about scale, right? But if you're, let's say, working in a big corporation and you know there are going to be these X users, it's not iterative. You know the design and then you build accordingly. So does that make sense?
Yeah. Okay.
Great. So when you talk about this scaling, right? So for example, if you're having lots of requests or if the load has increased substantially, like what are your scaling options? So one of those is a vertical scaling and horizontal scaling. And what basically vertical scaling means is that you add more processing power or RAM and all that stuff. And there's a limit to it, right? So a vertical scaling can only scale so much. You can only have so much RAM. You can only have so much processing power. So there's a limitation to that. When we build distributed systems, generally we are inclined more towards horizontal scaling. And the rationale behind that is that you can infinitely add servers and scale. So when you add more identical servers that can handle your request and distribute the load, that's horizontal scaling. When you scale up, let's say you increase the CPU or you increase the RAM, that's vertical. Right. So the next thing that we have is load balancing. And so what is load balancing, right? So you have these N servers that you have built out now, right? And basically what you want to do is make sure that somehow these requests distribute to these N loads kind of evenly or in a manner that is more appropriate, right? So that's where a load balancer comes in. And basically when you put in a load balancer, you can define certain configurations. You can say, hey, load balance it this way or the other way. I'm going to talk about what those ways are in the next slide. And then you can have, you can define health groups. You can define, maybe that server is not healthy. So you can have on the server something, a health, health API, and then the load balancer could be proving that health API, and that API stops responding. And then, maybe that server is not behaving. I should not route my request there. So you have dumb load balancers and smart load balancers depending on how you configure them. So what are the load balancing algorithms, right? I mean, on what basis would there be determine the load balance, how the load balancer should behave? Do folks on the call want to take a shot at, what could be those algorithms? Anyone? Natish, Ravi, Raghu? I see so many folks on the call.
One algorithm I remember is a round robin.
Right. So the most basic one is round robin. Basically, it's dumb. It just keeps sending everywhere. Any other algorithm? So like some of these algorithms, right? What is the least connection method? So if I have, let's say, N servers and like one of them has like, let's say, least connections, maybe I should route it to that one. Or maybe the least response time method, because maybe some server is just doing so well that their average response time is low. Maybe I should route it there. Or the server that is currently serving the least amount of traffic measured, right? Least bandwidth, maybe I should route it there. So again, when you're talking about systems, what you want to do is make sure what algorithm makes sense in that specific problem. We'll go through one problem as an example. But it's good to know all these algorithms that exist so that you can talk about it, right? And then of course there is round robin, like folks spoke on the call. You can just keep sending it to one another, and then there is weighted round robin. So let's say you have servers that are of different sizes, right? Then you can provide weights, and what that would mean is that, hey, this server is having more capacity, route more requests there, right? So that becomes weighted round robin. Like those are some of the algorithms that you can use, right? And the next question that could be asked is that, hey, is load balancer now a single point of failure, right? Because while you have these n servers, if there's just one single load balancer, does it become the single point of failure? I mean, of course it does, right? So, but there are again solutions or methods to avoid that. And one of that solutions happens to be, having an active load balancer and a passive load balancer. And what happens is that they each monitor each other's health. And in case the active goes down, the passive becomes the load balancer. Caching, right? So what is a cache? So, I mean, if you just go by the definition, caches take advantage of the locality of reference principle. Recently requested data is likely to be requested again, right? That's like the definition. But what does it really mean? So, for example, let's say you have some data, right, that's stored in some storage over the network somewhere, right? And now every time a user makes a request, you can either go take that network cost, make that call to that storage, get that data, and then show it. Or if that data is not changing, it's relatively static, you can probably cache it at some layer, right? And then the next step you would think is, maybe I should just cache it at my local disk, and that's, you save the network cost, right? So you're not making that call over the network, you save it on your local storage, you just get it from there. But what could be even more optimal? Maybe you don't want to save it on your local disk, and you say, I'll keep it in memory, right? It's a size that I can afford to keep in memory, and you keep it in memory, so that becomes super fast. So now when you're talking about caching, you're thinking about what layers. So if you just put it to disk, that's some optimization. You have removed the network cost. But then if you not even keep it at disk and keep it in memory, you save on not even your IO cost, right? So that's basically caching. You kind of take some data and keep it with you so that you can serve requests faster, right? And a specific example of caching would be content distribution network. You may have heard about Akamai or certain companies like that. So Akamai specializes in CDN. And basically what that means is, when someone asks for, let's say, a website, right, they're going to talk to the CDN servers and get the static content. So what CDNs do is they distribute the static content, keep it with them, like it behaves as a cache. So when you're requesting for a website, all of these static content can come from there. So you increase, the load, you make sure your load time is efficient. Like, is it making sense, or do you guys have any questions?
Yes, this is helpful.
Cool. So, right, I mean, again and again, what I want to emphasize on is building these, what we are doing right now while going through this theory is that we are building these blocks, and we'll use these blocks when we go and solve a problem. So it's important we know all of these in breadth, and of course, each one of these has a lot of specification. And you can go inside and read more, research more. Of course, there's a lot to cover. Great. But now that you have a cache, right? Of course, you need to update that cache, and there's a concept of cache invalidation. When do you invalidate that cache? What should be the logic, right? And so there are three primary known cache invalidation techniques. It's a write-through cache, it's a write-around cache, and a write-back cache, right? And each has its own perf gain and some kind of cons. So, for example, what is a write-through cache, right? Cache. So, if you are going to write something, right? Just a second. If you're going to write something, you will write it into the cache and the database at the same time. So, what that ensures is that your cache and database are in sync, right? But what that also means is that you have to write at two places, and that has a cost. So, for every write operation, you have increased the latency. So that's something that you have to think about. And when probably you're solving this with your interviewer, you need to bring this out. Hey, I know about this. This is the pro and con. What do you think makes sense? Probably this makes sense, right? So that is the write through cache. And then there's a write around cache, right? So it's similar to write through, but what you do is you directly write it in the storage. Now what happens is that if someone does a get on that kind of data, it will be a miss in the cache because the cache doesn't have it. the cache needs to go to the data store, get that data, and then populate. So your first read is sort of a cache miss, but eventually you have it in the cache. So probably it's a good trade-off where you're not writing at two places, you're just directly putting it into the storage. First read is not so good, but eventual reads are. So that is the write around cache. And but the write back cache is that you write it into the cache only and you don't persist it. So what you get is like super fast efficiency, but there's a high risk. So if you're, for example, if it's in memory and it just dies, or if, for example, it's in local disk and it dies, you technically never persisted that. So there is that loss. So there are trade-offs for each of these. What makes sense in what scenario? If you're okay with some kind of data loss, maybe you can have a write back cache and highest performance. Or if you're not okay with that, but you're okay with the first read being, slightly slow, then write around cache. Or if you are, if the requirement is, it should always be consistent, then you should go through write. So depending on what the requirement of the system is, you will decide what this cache invalidation technique should be. So we know what cache invalidation techniques are, but what should be the cache eviction policy, right? And all of these are again algorithms, basic algorithms that you learn in college. So, yep. Someone has any question on? Great, none. So, yeah, all of these are algorithms. Just like you have load balancing algorithms, you have cache eviction policies, and then you need to determine what makes sense in your scenario, right? I'll skip through some of these because these are trivial. First in, first out, last in, first out. Everybody knows. If you think I should elaborate more, please reach out. I'll talk about it. Least recently used is that this is not being used. It's the least recently. Maybe just remove it from the cache. Probably makes sense, right? Or least frequently used, right? The number of times this was used is less. So whatever makes sense. There's random replacement, but it doesn't make sense much generally. Then what we have is redundancy and replication, right? So if you see through these blocks and try to connect them, you will realize a lot of what we are doing is redundancy, right? So when you are trying to make a cache, you're actually building sort of a redundancy. I mean, this is not I'll talk more about what this redundancy is, but just to kind of increase your performance, you made that data come closer to you, right? So redundancy is a duplication of critical components. So if you have something, for example, we had a primary load balancer, we kept a passive load balancer. So that's like redundancy, but you need it because this is distributed systems, things can fail anytime, right? So to increase the reliability of the system is when you have these redundant systems in place. And there's also a concept of replication, right? So if you have data, let's say across two of these, three of these that need to be in sync, you need to replicate it and have that quorum and everything. So these are all just Uber level concepts that we all need. So we have covered, okay, so up until now we have covered, right, how we get a job, like kind of find those interviews, prepare for them. And then, some of these building blocks of system design, what they are, what they mean. And what I'm going to go through now is like the last phase and probably a little extended phase. And this is where we try to solve a problem, right? And it's a known problem. It's a very well-known problem. How do you design a URL shortening service, right? It's very common, asked in many interviews, and right. And what we're trying to see is that all these models that we learned, how do we talk about them during an interview, and what are the things that we need to think about? So it's great to know it's great to know just these concepts. It's important for you to think out loud and talk about them and connect them to solve a problem. So the problem that we are going to pick is designing a URL shortening service. Anyone knows what a URL shortening service is or has used? I'm sure people have used. Do you want to describe what this is? Yep, that's right. GOO.gl or bit.ly shortens long URLs as the name suggests. No rocket science. Yep, thanks, Piyush. So AK.ms as well. Yes, that's right. So AK.ms is Microsoft. We use it internally a lot. That's great. You know about it. Cool. So like Piyush mentioned on the chat, like URL shortening is just to create shorter aliases, right? It's a very interesting service. For example, if I give this webinar's link on, let's say, tiny URL, it will give me the short link and then I can share it on Twitter or somewhere, right? It's pretty interesting. And but if you had to design this system, what are the things that you need to think about, right? So with any system design problem comes a lot of structure on how you want to solve it. What are the things that you want to tackle first, right? And the first thing generally that comes up is like, what are the functional requirements? Right? You want to make sure you have clarity with your interviewer. Hey, what are the requirements that you're looking for, right? And so functional requirements, there are non-functional requirements, and then there are extended requirements. Good to have. So what are these requirements in case of this, right? So given a URL, our service should generate a shorter and unique alias of it. This is called a short link. This link should be short enough and easily copied and pasted into the application, right? When users access the short link, we should redirect them to their actual original link, right? That makes sense. A user should optionally be able to pick a custom short link URL. So I could say, hey, I want it to be some, ABCD or whatever, and that could be like the short link. And then links, basically after some time of some standard default time span, you can say that these links expire, and maybe have that configuration. Customers can say, I want it for so and so duration. So those become your functional requirements. You want to make sure what the interviewer is looking for. What I want to call out specifically is that generally when you're going through the system design problem, almost always your interviewers kind of have already a solution in mind. They are going to nudge you and give you hints, but it's basically on you to make sure that you cover everything and you get the most out of them. So you would want to align with that, and of course feel free to talk about everything that you know and what makes sense here. So those are the functional requirements. The non-functional requirements would be like the system should be highly available. This is required because if our service goes down, basically your direction would work. So all those folks who use our service to sort of give the short URLs, that won't work. So that becomes a non-functional requirement, or it should happen with real time with minimum latency. And the extended requirements would be, it would be great to have some analytics, right? All softwares will eventually require some kind of analytics so that you can determine how to make improvements, where to make improvements, and all that, right? And maybe it would be great if our service is accessible via REST APIs. So those are the requirements that we have while we try to solve this problem, right? Once you have the requirements from your interviewer, what you're going to think about next is, okay, anyone wants to take a call at what could be like the next thing we think about, right? So we have an interviewer. He has a functional requirement. You have got that clarified. How do you go next? What do you do next? Sure, Ritesh, go ahead. Ask question. Architecture, right? Sure, all these are right. But one of the things that, at least the way I'm thinking about is that I want to have is, what are the next? Like I have the functional requirements, but what is the usage going to be like, right? I mean, if there is really not going to be that much usage, or it's probably an internal service only meant to be used by this internal folks, the way you design the system will be very different from, let's say, if this is a public service, and right, its requirements are several times more. So the next thing that generally comes is capacity estimation and constraints. You would want to understand what is the capacity going to be like, and so that when you talk about your systems, you can talk about that. Fit it on a node, whether it will make sense to fit it across nodes, right? Those determined by these numbers. It's a little bit of maths, but it's trivial maths. It's not that hard. So I'll go through this. Right. So our systems will be read heavy because we are a URL shortening service. Someone's gonna come and register their URL once, and then there are like n number of people that are gonna use it, right? That's how you will like talk about it. And then you say, probably it's a good idea to make it 100:1 ratio. One thing that I want to call out is these assumptions that we make. They need to be somewhat reasonable. They'll come with more practice, but there's actually a next step. Even these assumptions can have their own research, right? You can go into do some research. This is the use case, or you have done some study. But let's park that for now, and let's just say you have these ideas about what these numbers are going to be like. You come up with them, something that makes sense, and then you design your system with that. And I think that's okay, because what they are looking for is how you design your system. It's great if you can think about how these numbers come up, why these numbers come up, but that's like part 2, right? I mean, that's good to have. So, right. So what we are going to assume is that there's a 100:1 ratio between read and write. And so, I mean, again, some random number out there, we say like there are 500 million new URL shortenings per month, right? So what is the basically expected, redirections during that same period? So if there are 500 million in a month that people register, and we have a ratio of 100:1, that means 500 million into 100, that makes it 50 billion, right? So the number of redirections that we are looking for is 50 billion in a month. The number of registrations we are looking for is 500 million in a month, right? Then once you know that, like, what will be the queries per second for our system, right? So it's 500 million. So you divide that by, let's say, 30 days, 24 hours, and 3,600 seconds, then you get 200 URLs. And it's interesting to talk about it. I mean, it's interesting to think about it, that you're thinking through all these scenarios, that there are going to be these many queries per second. It's good to know, and because your systems are going to have some constraint, and they should fit in the problem you're trying to solve, right? Yeah, and then considering the same 100:1 rewrite ratio, the number of redirections are going to be like 200 into 100. Right? So everyone with me till now, I'm going to talk more about constraints, but I want to make sure everyone is following.
Yes, yes.
Right. So again, now that I'm talking about estimates, the another interesting aspect to think about is, how many kind of estimates are there. So this is what we did, is a traffic estimate, right? The next one could be storage estimate, right? Fine, we know this is going to be the traffic. This is how the traffic is going to look like. But how much storage are we going to consume, right? That could be like the next question. So again, you can go through this. Let's assume we store every URL shortening service, right, for 5 years. And considering we're going to have 500 million URLs every month, so the number of objects, right, that we're going to have is like 500 million into 5 into 12, right? Because we have 500 million per month into 12 and then into 5. So that many, the 30 billion records is something that we're going to have. Right? And then the next question could be that, hey, what is this each record size going to be like? And let's just take another number, let's say 500 bytes, right? So if you take 500 bytes, it becomes 15 TB. So now you have a storage estimate. Of course, this number that you come up with should also be well defined when you design your objects, right? So you will know the exact numbers. But for now, you can just take a ballpark number and say, you know what, we need like 15 TB of local storage, right? So 15 TB of storage. So now you know what the storage. So you know about the traffic estimates. You know about the storage estimates. So the next estimate is on bandwidth, right? And so what is the bandwidth requirements going to be like? Like what would be the network requirements you would need? So since we have 200 new URLs every second, right? So total incoming data for our service will, let's say, be 100 KB per second. Yeah, so 200 into 500 bytes makes it 100 KB per second, right? And for read requests, again, there are going to be 20K requests. We saw that in the previous estimations that we made. And since each of those requests is going to be 500 bytes, it's going to be 10 Mbps, 10 MB per second, right? And then there are more estimates coming up. And the next one is memory estimates. So we did kind of storage estimate, and right, tomorrow, if you want to talk about, if you want to have a cache, right? Because a lot of these requests might be for the same URLs. Does it make sense to build a cache? And then if it makes sense to build a cache, then what would be the memory that is required, right? So there is a very famous 80-20 rule, which says that 20% of the URLs will generate 80% traffic. So we would like to cache these 20% of these hot URLs and serve them fast. And if you go ahead with that assumption, right, considering you have 20K requests per second, we'll be getting 1.7 billion requests per day. And if you want to cache 20% of these requests, we will need around 170 GB of memory, right? And the thing you need to note here is that a lot of these requests might be duplicate. So the usage will be way lesser than 170, but it's still good to have a higher number. So these are some of the estimates. We thought about traffic, and then we thought about storage, we thought about memory and all that stuff. So it's good to talk through your estimates, right? Have these mental pictures in mind that, hey, I'm going to talk about these estimates. What does that mean, right? And the next thing that comes up is you have you define the functional requirements, you have defined your estimates, and then now you're going to define your API. How is that going to look like? And again, defining an API is pretty straightforward. You can think of it as a function call, like in simple terms. And what it is like is, let's say you want to create URL, right? So we'll have an API def key, so some key to identify that user. And then there will be like, what is the original URL that the customer is trying to kind of shorten. And if he has any custom alias that he wants, or if there is a username, right? And if there's an expiration date for that. So these are things that the customer can set. By default, they are none, and then you can have your algorithm accordingly, right? And what we would return is a shortened string, or basically, if there's some issue, we'll just return some error code. So that's like a function definition, sort of like how these APIs are going to look. And if someone wants to delete that URL from this service, they're just going to call it delete URL, API or something like that, and it's going to have the def key to identify that, and then it's going to have the URL key, and basically that would remove that URL, right? So we have defined the system APIs now, so we're gonna think about how do we actually, right, solve this problem.